Hi, welcome to my channel. My name is Changjiang. I'm going to introduce a work about improving mapping for sparse direct solvers, a trade-off between data locality and load balance. Sparse matrix solvers are going to solve the linear system AX equals to B, in which A is very large and sparse, lots of zeros included. Generally speaking, there are direct methods and iterative methods. In plastics, a direct matrix solver considered in this work. The solving is composed of a sequential analyze step and a parallel factorization and solve step. We focus on the scheduling and mapping phase in this work. At a cross-grain level, the computation is represented as a tree of supernodes, where nodes represent computational tasks and edges represent data dependencies. If we room the supernodes, we can find that the supernodes are composed of many small tasks, which themselves form a small, direct, acyclic graph. At the scheduling and mapping phase, we map processors to tasks. The first step is to map a subset of processors to supernodes. Then a processor in the set will be selected for each task of a supernode at the second step. In this way, we can exhibit tree level and load level parallelism and reduce the scheduling complexity. Let's see the first step. Proportional mapping is a widely used classical approach to solve this resource allocation problem. Follow a top-down way, it assigns processors to a branch of nodes according to their relative weight. Let's see an example. On the left-hand side, we have a tree of supernodes. The weight of the whole tree is 100. At the beginning, all processors from P0 to P8 are assigned to their root node. Then half processors are assigned to the left branch because its weight is exactly the half of the whole tree. The same goes for the right branch. This process continues recursively until reach the leaves of a processor, or a processor is assigned to a whole branch. Proportional mapping is good at preserving data locality. A processor may be assigned to a node and its ancestor, so we do not need to move the output files. But it's bad at node balance. Processors can be used only for the branch they are assigned to. Different branches have different parallelism capability, even if they have the same weight. Some branches are hence idle, some processors are hence idle, while other branches cannot benefit from these processors. Let's see an example. So we have 10 processors. We assign all them onto the root. According to each branch's relative weight, proportional mapping maps 4 processors to the left branch and 6 processors to the right branch. The right branch only has 5 tasks, so processor P9 is idle. However, the left branch has 5 tasks. One of them can be assigned onto processor P9. An intuitive solution is to assign all processors to all tasks. We call it all-to-all heuristic. It solves this node imbalance problem, but it's complex and incurs lots of data movements. This work is going to answer the question, how can we improve the node balance while keep good data locality? We can solve it in the second step. Let's say the second step. The aim of the second step is to decide the precise mapping for each task. In plastics, this is done by simulating the actual factorization based on the prediction of both the running times of tasks and of the time needed for data transfers. After the first step, as you can see now, a set of processors has been mapped onto each task. Each processor is equipped with 2 priority queues, ready queue and waiting queue. Ready queue stores tasks that have received all input files. Waiting queue stores tasks that have received part input files. Tasks inside will be sorted by an increasing ready time. Since leaves don't have any dependencies, they are in the ready queue at the beginning. Each processor has a ready time. It represents when this processor finishes the current job and can start another job. Each task also has a ready time. It is calculated as the time it receives all input files from its successors. At each step, the scheduler compares the first task of all ready queues and selects the one who can start earliest. Then it updates ready time of processors and queues. So right now, we can select task M, task I, task H, task J. We randomly select one because they all can start at the same time. We select task G and we run it on processor P0. Then we update the ready time of processor P0 as the finish time of task G. And then task C will be inserted into waiting queue of processor P1 and P0 as they receive part input files. Then we select the task who can start earliest, task H. We schedule it on processor P1. Then we select task I. We update ready time of processor P2 and the waiting queue of processor P2. We continue this process. At each step, we select the tasks who can start earliest, and then we update the ready time of the processor and the queues. So right now you can see that the ready queue of processor P0 and P1 are empty. We continue this process. We schedule task A, and finally we schedule task R. So then the whole mapping is finished. You can find the idle states of processors very easily. We can find that processor P0, P1, and P2, they have some idle times, idle slots. So if we can reduce these idle slots, then we can make sure that each processor has as many work as possible. Let's roll back to where the idle comes from. At this step, ready queue of P0 and P1 are empty, so no task will be mapped onto them. If we can steal some tasks from other processors, processor P0 and P1 may have something to do. Let's take processor P0 for example. Next task will be mapped onto processor P0 is task A. The idle slot can be calculated as the ready time of task minus the ready time of the processor. To reduce this slot, the task we steal should start earlier than task A. But task B can start earlier, hence we schedule task B onto processor P0. The idle slot is then reduced. The same analysis goes for processor P1. And finally, the task A can start earlier. Let's summarize the steal technique. At the moment, if the ready queue of processor P is empty and the ready time of the first task in waiting queue is strictly larger than the ready time of processor P, we predict that there will be an idle slot. To reduce this idle slot, we copy tasks from neighbor processor's ready queue. In order to reduce their movement in a distributed environment, we steal tasks that are on the same cluster. For testing our heuristics, we conducted the experiment on 34 large sparse metrics from various fields. The scheduling strategies considered include all-to-all as a reference, and the proportional mapping, the classical scheduling algorithm, the one we propose, steal, and a variant that prefers stealing tasks on the same MPI node, steal local. Let's check the results. Those two figures show the data movements between different MPI nodes. The left figure is the number of communication. The right one is about the volume. X-axis shows the different MPI settings given. For example, 2M12 represents 2 MPI nodes and 12 threads. The number and volume of communication of steal is the same as proportional mapping and far lower than the reference algorithm all-to-all. And those two figures show the performance on the data movements inside an MPI node. Steal and steal local have more data movements than proportional mapping, but less than reference heuristic all-to-all, especially the number of data movement. Those two figures show the simulation cost. We can see that all-to-all is far costly than others. Steal and steal local have almost the same cost as proportional mapping. Steal and steal local are slightly faster than proportional mapping, according to the estimated factorization time. Finally, let's check the real factorization time in a shared memory environment. As you can see that still has the same performance as all-to-all, and is slightly better than proportional mapping. In conclusion, the algorithm we proposed reduced the communication frequency and volume, and slightly reduced the final factorization time. In this work, we revisit the classical mapping strategy, proportional mapping. To solve the load imbalance of proportional mapping, we proposed the steel technique-based dynamic scheduling algorithm. Extensive experiments on real software plastics shows that our method achieves a good trade-off between data locality and the load balance. For the future work, we expected a better performance of our algorithm in a distributed environment. As the communication is more expensive, so we will perform further experiments on distributed platforms. We also plan to propose some novel strategies to further improve performance. Thanks for your attention.